Yuri. We just met just a few weeks ago, in Italy, and also see some new friends, and also thank everybody here to resist the sunny beach to be with us. And today I'm going to share with you our work on mitochondrial quality control, which we think this is very important for the quality of our life. Just see. No. Okay, I assume everybody knows mitochondria are important organelles that serve as a cellular powerhouse to produce ATP to support its life-supporting system. And the mitochondria are also the organelle that produce the heat that keep our body warm, and of course it's a center of free radical generation and also the metabolism in the cell. And also mitochondria controls immunity and apoptosis, a specific type of cell death. So to do that many jobs, mitochondria are highly dynamic and they go constant fission and fusion and also turnover. So as you can see, the mitochondria kind of very sensitive to many types of stress. And this is in culture dish under microscope. You can see the red fluorescent labeled mitochondria upon certain type of stress. From it can change its shape. So it through this we call fission and fusion process. Okay, so this tubular mitochondria undergo fission to become a smaller one, and they may be reunited to form a longer one or the network. And the damaged mitochondria could be removed, or could be removed through a process we call autophagy, and this can be replenished by the new biogenesis of mitochondria, so that keep mitochondria in a homeostatic condition. So almost 20 years ago, we get interested in how this mitochondrial dynamic is regulated, and we search for new molecules that may regulate this process. One of the protein we identified at the time called FUNDC1, and this protein we just only know that it's a mitochondrial protein from the signature motif it has, and without knowing function. The name is interesting because the first three-letter fun and the first four-word fun plus fun. I think that's very important for research, right? And what's surprising, one of my students did at that time, when he just simply overexpressing the gene in HeLa cells, and he see this mitochondria become fragmented, where the labeling cell, without overexpressing, you see the mitochondrial network. And he also found that the GFP labeled LC3 become aggregating. And this was widely, GFP labeled LC3 was widely used as autophagy marker. And it was surprised at that time that how a mitochondrial protein can do the job, because at the time, 20 years ago, we know that GFP labeled LC3 as a marker of autophagy only appears when the cell undergoes starvation. But in our case, the cell cultivated in perfect fine condition, and only expresses FUNDC1 causing this GFP LC3 aggregation. And it turned out that this FUNDC1 actually induced a specific mitochondrial autophagy. So we did immunogold labeling EM analysis to show that the autophagus membrane can enclose mitochondria just within. So as you can see, the gold particle just within the autophagosome. So and to take long story short, we identify this FAMIC1 as a mitochondrial outer membrane protein, which is at N-terminal, has very specific motif. We call it LER motif that can specifically interact with LC3 to bring the LC3 is an important molecule for autophagous membrane formation. So through this interaction, it can bring the autophagous membrane to the chronicity of damaging mitochondria. We did the structure analysis to clearly show that the LER motif is important for interaction with LC3. And when we mutate or delete this LER motif, it no longer function to induce mitochondrial autophagy. And in the past many years, or 10 or more years, we try to figure out how this process be regulated. We know that when mitochondria become damaged, it can activate the process. Under normal situation, the mitochondria may be small portion damaged, but it's hardly to see. Only until the damaged mitochondria can be removed through this process. So we try to understand how this process is regulated. It turns out this FAMIC1 as a mitochondrial outer membrane can be highly regulated. In this case, by phosphorylation, also by ubiquination, acetylation, and degradation. All this process, we have a paper to show that. So through this regulation, the post-translation with modification, we see this FAMIC1 can, its interaction with LC3 can be tightly monitored, and in response to certain type of stress, say in response to hypoxia or stress condition, it can dephosphorylate and to activate this process. All this paper has been published. For the sake of time, I don't have time to show in all the detail. So how do you know that the FAMIC1 involved regulating this mitophagy process? The next question comes to our mind is that how this mitophagy process is balanced with mitochondrial biogenesis. The cell must know how many mitochondria is needed and how to remove the damaged one and to have new one to replenish this removal. So people already know this must be balanced, but it's not clear that how this is regulated and at the molecular level. Because as you see here, the mitochondrial biogenesis are regulated by a group of transcription factors, including NRF1 and others, where the mitophagy, can be regulated by autophagy genes and adapters like FAMIC1 and PIN1 pocket and others. So how this process can be regulated at molecular level, I do not know. To address this question, we turn attention to brown fat. People know, and just a simple cold stress can induce mitochondrial biogenesis in animal and also in our body. So, so what we did is just have this mice under cold exposure. You can see mitochondrial biogenesis occurs. You can see the mitochondrial protein get upregulated, mitochondrial DNA, the number get increased upon the cold stress. And what's surprised is that FAMIC1, which is a mitophagy gene, is also upregulated. This is kind of counterintuitive because if in cold stress you need more mitochondria, so you should stop removal of mitochondria. But FANDH1, what the mitophagy with protein, how this happens, and it's turned out that indeed, and just cold stress, we can see that mitophagy occurs, and when you lock out FANDH1, the mitophagy was luckily blocked. So. It turned out that the mitochondrial biogenesis, as mentioned, can be regulated by this PGH1 and NRF1 process, and it's also involved in the transcriptionally regulated FANDH1. So as you can, and also we found that when we lock out FANDH1, it can feedback regulated PGH1 stability, as you can see here, and this wild type mice or FANDH1 lockout mice, you can see under normal condition the mitochondria level is low, and upon cold stress you can see mitochondrial biogenesis occurs. But in the absence of FANDH1, the mitochondrial PGH1 level is lower, so the whole mitochondrial biogenesis can be slowed down. So that we think FANDH1 not just only regulate mitochondrial autophagy to remove mitochondria, but also regulate mitochondria turnover, so that so that this process can be tightly monitored in response to stress, and also in response to stress or our in our body. So next question is that whether this process is has a physiological or pathophysiological consequences. People already propose that defective mitophagy may causing the aging associated diseases, but people don't know it's just an association or just it's any causal consequence for defective mitophagy causing is the causal effect for the aging associated diseases. So to do that, we generate knockout mice, and surprisingly the mice are viable, very happy, no problem. But upon certain type of stress, when we feed the mice with high fat diet, it's getting fattier. And also if you challenge the mice with carcinogen or other ischemia reperfusion condition, you can see problem. Basically, that tells us that the FANDH1 mediated mitophagy may be related, but it seems not the causal reason for this diseases. But people know that if using the germline lockout of certain gene, there is maybe a compensation mechanism, so that you don't see much effect of these lockout mice. So we then using the inducible lockout mice to see if there's any effect, and we use this homeostasis induced lockout after the mice was born. So we see now that just the inducible lockout of FANDH1 endothelial cells can develop spontaneous pulmonary hypertension. So that as you can see, just the lockout of FANDH1 endothelial cells, you can see the blood pressure become higher in mice, and also the endothelial cells and also the blood vessel become thicker, and so that causing the problem. So people already know that the pulmonary arterial hypertension mainly caused because of the damage of the endothelial cells and also the proliferation of smooth muscle cells. So the question for us is then how FANDH1 in the endothelial cells causing this problem. So what we did is, like many others, we do the single cell analysis and to see what kind of regulatory mechanism. So from this analysis, it turned out the endothelial cells, in the absence of FANDH1, become kind of senescent. We see this gene expression of senescent gene are expressed including P53 or P21, and this cell under microscope, maybe you don't see clearly, but believe me that these cells become senescent as stayed by the Bettel's analysis, and then we try to understand how the senescence endothelial cell contribute to this phenotype. And it turned out that the senescent endothelial cell can secrete this IGF-BP2. How much time I have? And this may promote the proliferation of smooth muscle cells. And if we use antibody to block that the IGF-BP2, you can alleviate this symptom. And to cut long story short, what we found that FANDH1 in endothelial cells that has an important function for cellular metabolism, and in the absence of FANDH1, the endothelial cell become reprogrammed and also getting into the senescence, which secretes this IGF-BP2, which then subsequently stimulates the proliferation of endothelial cells. I don't have much time. I'm going to skip this. And the last slide, just because you look out the gene maybe have many different functions. So what we did here is just using a lock-in technology, just mutate this tyrosine residue into phenylene or tryptophan, which we know that can interact with LC3. The tyrosine, we know that interacting with LC3. This mutation causing the gain of function of FANDH1, where if we mutate this tyrosine into alanine, there's lots of function, and this can clearly show you that in the gain of function phenotype, the mutant, you can see the mice, have lower body weight, have much better performance, and this clearly tells us that mitophagy is important for our healthy span. So take-home message is that this mitochondrial protein FANDH1 regulates mitochondrial autophagy and also mitochondrial turnover, at least under the physiological condition, and we think this turnover could contribute to the quality of our life. Okay, with that, let's thank the lab members who do the job and also the funding agencies. Thank you for your attention.
One, two short question.
A great talk.
questions. The first one is, I'm very surprised that you say preventing C1 knockout the crosstalk with biogenesis, the PGC1 also downregulated. So what is the meaning of that? Preventing C1 knockout, you have bad mitochondria. And in this way, but there are other mechanisms that can turn over the bad mitochondria, right? And why the cell should decrease mitochondrial biogenesis?
So yeah, that's a good question. So mitochondria, the cell must know how many mitochondria to keep. Yeah, to have sufficient energy and all these metabolic processes. So it's very surprising that when mitophagy was defective and this kind of feedback regulated
it's very
stability.
Interesting. What's the meaning?
That means mitochondria. First, this mitophagy process is kind of it kind of controls this mitochondria turnover. Yeah, so that mitochondria can constantly remove the damaged one where they keep produce the new one. So that's the key point. And the molecular mechanism how FNDC1 try to regulate the stability is not clear yet. But we did know that the PGC1 is a master regulator and it undergo say the ubiquination and also other type of modification for its stability. Yeah.
The second question is related to the phenotype of EC and DC1 knockout. And so those phenotypes are very interesting, but do they correlate with mitophagy or there are other kinds?
Yes, we did all sorts of assay. Yeah, the paper I think is going to come out.
So it's due to mitophagy.
Yeah. So we did a number of assays like in the lockout mice. If we add back by the AAV injection, if we add back the wild type one, it works, and if the near motif, mutant one, not function. So we did a number of assays, to show that. You really have a comment? Have a question? Yeah.
How do you try to knock out this form C1 in other cells, not only in mitochondrial cells, and also you produce senescence in that case?
That's a very good question. So we did a number of assays to come to this point. Yeah, when we do this knockout in the smooth muscle cell, and others, let me think. In the heart, we are currently, some of this ongoing. But it's good point. Your point, I think is that the mitophagy or the FNDC1 mediated mitophagy is, I think it's in the cellular context dependent, not regulated in the cellular context dependent manner. Yeah. Your question?
I wanted to ask if the Lear domain is also needed for the effect on biogenesis. So is everything mediated through the Lear domain, or certain functions operate without Lear domain?
In our situation, I think the Lear motif dependent. So, and as we see have this Lear motif mutant mice to clearly show that mitophagy. I don't have time. Yeah, if you this the gain of function mutant, you see much mitophagy higher, and this in the action with Lear motif, mutant to alanine is lots of function. So, and the whole mice behavior quite different. Yeah, this kind of have very high, better healthy span. Yeah. call it, we create a marathon mice. It kind of running, lipid is skinnier, but running much better. Yeah.
Okay.
Okay, thank you.
Thank you.